Lecture 2, Review of Processes and Threads. In a prerequisite course, should you have taken them as per the standard program, we covered 3 important things that are relevant to the operating system. We talked about processes, we talked about threads, and we talked about hardware. Here, we're going to take some time to review these things and make sure that we're on solid ground before we move on. A lot of this looks and sounds almost exactly like we talked about in ECE 252. Maybe we look at it a little bit differently because we are coming at it from a sort of different perspective now that we are thinking about it from managing it as the operating system as opposed to just how we have to live with what the operating system gives us. But nevertheless, a lot of this will seem like review, but I think it's important that we actually take some time to review these things and make sure that we have them fresh in our mind and are feeling prepared to move on. Okay, so process and thread. Well, we've talked about a process in some detail. We said a process is a program in execution. And a program is the compiled executable. Those are the instructions. There's associated data with it. There is a current state, and it has some associated resources that are necessary to execute the program. And we've talked about the kinds of resources that we need, things like memory or a hardware device or something like that. All of those things qualify. And as you know, also 2 instances of the same program running equals 2 processes. If you have 2 windows open for Microsoft Word, even though it's the same executable program, they are separate processes, and 2 users who use Firefox at the same time on a terminal server are, again, interacting with 2 different processes. Right? And you probably also saw this diagram where we have sort of side-by-side 2 documents, document 1 and document 2. And both of them are instances of Microsoft Word, but they are respectively different processes, and they have different process IDs and are managed separately by the operating system. Speaking of which, we also learned in the past that the process control block is the data structure that is used for managing the process. And the process control block is not super exciting as a data structure, but it just contains whatever the operating system needs to know about managing the program. And in the past, we didn't work directly with process control blocks, and we talked about them, so we had some understanding of what's going on, why do process switches happen, how do they work. But now at this stage, actually, as the operating system, we are responsible for managing these and understanding how they work, and keeping track of the processes with a process control block will be important in several of the things that we do. But when a new process is created, right, a process control block is created, and we update it as is necessary, depending on what is happening. And it can be thrown away when the program has finished executing and has cleaned everything up. We learned about zombie processes and stuff like that, and cleanup also previously. And the blocks need to be held in memory and are maintained in some sort of container, some sort of management structure. Maybe it's a list. We'll see as we get a little further in the course that maybe it's actually several, and the kernel keeps track of these. Okay, and the process control block, we said, needs the following things, and as I say, it's important that we revisit some of these because, well, now we're going to make or modify process control blocks or work with them. But every process has a unique identifier. For a Unix system, the identifier is a relatively unique integer. And I say relatively unique because no 2 processes at the same time can have the same ID, but IDs can be reused eventually, usually after some period of time. Right? It is a simple integer in this case. It increments when a new process is created. The counter will restart when the system restarts, but all we need is a unique identifier. 24601, I think, is the example that I used previously. And then we have the current state. And we talked in some detail about the different possible states that a process can be in. And yeah, tracking that here is relevant because, well, we need to know, is this process ready to run? Is it blocked? What's going on with it? And knowing that is going to be important in terms of making decisions later on. Like when we get to scheduling, right? You can't schedule a process that is not ready to run. And how do we know if a process is ready to run or not? Well, we know that by keeping track of its state. And then we have priority. And we didn't really spend a lot of time talking about priority in this regard. I mean, maybe we talked briefly about it when we were considering, say, deadlock or something like that. But priority is just a simple ranking of how important is this process as compared to others. The priorities are relative and not absolute in any sense. And these priorities are used in making decisions by the operating system, right? Like which processes run first, or if two of them want the same resource, which gets the resource right now. We'll talk about that sort of thing again much more when we get to something like scheduling, but keep in mind that priority becomes kind of relevant for other things as well, such as memory allocation. Now we have program counter and register data, and these are marked with a little asterisk, and it's just our way of saying these are not always kept up to date. They're just updated when needed. State changes whenever state needs to change, but program counter is only updated when the state of this process is being saved, because we are currently running it and we need to switch to a different thread or a different process. That's when we would update the program counter and the register data as a place to save it. We'll also see there isn't a strong requirement to store these in the process control block. You can like throw them in a stack, or you can put them in some other data structure, or put them somewhere else if you want. It's just common and for the sake of a simple implementation to put them in a process or thread control block, and that's what's recommended, at least in this approach. And then we have memory pointers, and these are pointers to the code, the executable code, the data, any memory that the operating system has allocated to this process by request. We know to some extent that the operating system must keep track of this, right? When you allocate memory, you get memory, and if you try to access something that is outside of the memory that you've been allocated, well, you get a segmentation fault. And we'll talk about it some more when we get to the actual memory units, but this is a way to keep track of memory, is to associate it with a process control block. Another way that we know that memory is something that the operating system tracks for us is when a process exits, even if it is not cleanly, even if it is without calling any deallocation calls, the memory that process has claimed is returned. It is not tied up. And so, yeah, even if we don't deallocate that memory, it does eventually get returned to the operating system. It's not ideal strategy, but it does indicate that the OS remembers, if you will, what memory has been assigned to a particular process. I/O status information. Any outstanding requests, any files that are open, any I/O devices currently assigned to this process, all of those will appear in the process control block, because again, the operating system has to know about them somehow, but also needs to free things up when the process exits. Right? Normally we expect a file to be closed, but again, if you exit the program without closing the file, the operating system will close the file on your behalf. So it has to be kept somewhere. And then finally, there is the accounting information. And the accounting information is just stuff about like how often has this program run, what is its use of resources. In a super simple operating system, maybe you don't care. Maybe there is actually no need to keep track of this, particularly in like an embedded system where the goal of the system is to do one thing, and we don't really care like what it's been doing otherwise. Then maybe you don't keep track of those things because it's less overhead to just not care. But most likely, sort of any general purpose operating system will at least make some effort to keep track of these are the resources that have been used by which process, and it's certainly very important in something that's like a multi-user system, because we need that to know, is somebody using more than their fair share of resources. And we talked just recently about security and that sort of thing, and protection. And one of the ways that we could identify that something is wrong is a process is using way more resources than we would expect. And the only way we would know that is if we're keeping track of it somehow in accounting information. And you also saw previously a visual representation of a process control block, and it's just a data structure. Nothing super exciting there. Okay, and we've said also that the purpose of a couple of the fields, particularly the program counter and the context information or registers, is used as storage. So we talked about a switch between processes, and we said, okay, I even showed this diagram where process P0 is executing. We have an interrupt or system call, and the operating system is responsible for handling this interrupt. Oh, it's a trap. And waking up and saving the state into process control block 0. And then there's that 3 dots in between save state into PCB 0 and reload state from PCB 1. I think it's pretty obvious that what happens there is this is a scheduling routine. The operating system is making a choice about what process is going to be selected to run at this point. And for the sake of the example, we said, okay, it's going to choose process control block 1. So process 1 is then selected, and it is going to continue executing from wherever it left off. And then it will execute for some time until there is an interrupt or system call. And again, the operating system takes over, and we will save the state of process 1. There'll be some scheduling. We're going to imagine in this case that it chooses process 0 to run next, and then process 0 is restored to execution. Again, there's a scheduling decision. A few things to note. Number one, the saving the state of process control block 0 is kind of non-optional, right? Like when we go to the interrupt and do the interrupt handling, we're always going to suspend that currently executing process and then try to make a decision about what to do next. It is entirely possible that we choose process 0 again. There's no reason why we have to switch between processes if P0 is more important, or it's the only process that's ready right now. Or for many other reasons we might choose process 0 again, then there's no need to switch because, well, we would only switch if that makes sense. Again, in a scheduling discussion, we will talk about situations where it makes sense to switch between processes. Do we take turns? Do we not? All of those things will be determined by scheduling policy, but also the processes that are currently available and ready to run. And then restoring the state of whichever process we're going to restore is relatively straightforward because we just copied everything into memory, and then we can just copy it back and assign the registers on the CPU, and we're ready to go. So that part is not too new to us. We should have covered this early on in ECE 252, except we just said, yeah, this is what happens, but we didn't really say it's our responsibility to make it happen. But now we're on the other side of that. And we also talked about the circle of life. And upon creation, the operating system will create a process control block, which implies that process control blocks can be created and destroyed. Upon creation, right, that's allocation of a new process control block and initialization with some values, set variables to their initial values, set initial program state, set the instruction pointer to the first instruction in main, and add the PCB to the set. After the program is terminated and cleaned up, then maybe we need to collect some data, summary of accounting information, something like that, remove the process control block from the list of active processes, and we carry on. There are 3 main events that may lead to the creation of a process, and we covered all of them. System boot up, user request to start a new process, and one process intentionally spawning another. So, okay, we've talked about each of these in some detail. On system boot up, right, the operating system will choose to start various processes, and many of them may be its own internal functionality, some of which may be foreground and some of which may be background, right? The login screen is a user visible process. Others that collect accounting information are background ones, and we don't necessarily interact with them. You've already worked with lots of these. If you've logged into a Linux system, SSH client that you use is a user interactive program, and it connects to SSHD the background daemon or daemon, depending on your preferred pronunciation, that responds to the request and allows you to log in remotely to said system. So, okay, we're familiar with those. Users, of course, can start processes whenever they like, no matter what operating system developers might wish. Users are just kind of like that. They will start processes when they want to, even if the system is very busy, even if there's a lot of contention for resources. And then we talked about one process spawning another. So we talked about the use of fork and how we can effectively ask a process to create a child process. And we ended up with lots of examples around this idea, so I don't think we have to go into it too much. Right, whenever you click an icon, you can create a process. This image still bothers me, but yeah, eventually most processes will die, and we also discussed that this could happen in one of several ways. And there's normal exit, which is voluntary, error exit, which is voluntary, fatal error, involuntary, and killed by another process, involuntary. And we've covered, I think, to a great extent, all of those things. When your program reaches the end of its execution and you call exits with 0 at the end of its execution, that's a normal voluntary exit. You are choosing to exit, and by exiting with a return code of 0, you are saying this is a normal exit. Everything is fine. We should also be familiar with error exit. And error exit is also voluntary, where we choose to exit because there's a situation that we simply don't want to handle. And the program was provided wrong arguments. Like we can just exit at that point, right? Some state that we don't like has taken place. We can say, you know what, we don't want to continue. It's time to exit, and that is perfectly fine, right? That sort of thing is easy. We just use the exit system call, and the program will terminate at our request. We've also talked about involuntary termination, fatal error, stack overflow, division by 0, segmentation fault, all of those sorts of things. Now, some of those are generated by the hardware, division by 0, for example. Others come from the operating system itself, where the OS is going to send in a segmentation fault if you try to access memory that does not belong to your process. And that's perfectly fine. We're familiar with sort of how that works from the user process side. We'll see when we talk about memory how to make that happen. And then we have killed by process, which is involuntary. And we learned about the kill signal, and we learned about the idea of like sending signals between processes. One process can terminate another if we think it makes logical sense. You use the kill command or the kill system call to send a signal, and there are restrictions on that, but it does work, right? User or process must have the rights to actually make that happen, and system administrators obviously can do this, as well as the operating system itself can terminate a process if it thinks it has gone rogue. We may have thought of several scenarios in which this makes sense, like if a process is using too many resources, you terminate it. That's something the operating system might choose to do, even if that's not very common for a commercial operating system. Okay, and we also talked about the 5-state model. We talked about the 7-state model as well, but then we got talking about threads and what have you, and we talked about just the 5-state model is applicable to threads, but the 7-state model applicable to process. Not every system follows exactly these things, and Unix actually has a few more states than this, but the idea is well captured by this diagram, right? We have the various different states. The new state, when a process is created, it is new. It hasn't run yet, but it's being created. And in fact, we said that there are 8 transitions: create, admit, dispatch, suspend, exit, block, unblock, and reap. The name's maybe a little whimsical in some cases, right? But admit is a process in a new state is added to the list of processes ready to start, so it's put in the ready queue. Dispatch is when a process that is not currently running begins executing. So when the scheduler chooses to run it, then it's dispatched. When it gets blocked for some reason, well, it goes to the blocked state. When it's unblocked, it goes back to ready. But even a process that is not blocked could be suspended because it's just time for another process to have a turn, so it goes back to the ready state. And we'll see some more about this when we actually talk about scheduling. And a process can exit, and we also said, well, it can exit at any time, so there are like invisible transitions to terminated wherever we go in this diagram. Yeah, if a process is killed, then that could happen at any time from any state. And we said also there was a 7-state model that represented the process because it kept track of the idea of whether the process was blocked or just blocked and swapped. So swapped in this case means that it's not in main memory. So blocked and swapped is a process that is not only blocked, but it needs to be moved into main memory before we can continue its execution. We'll see as we get through the topics about memory and scheduling, the meanings of the different states and sort of how to make them work, and whether or not we even need these particular states. But we'll save that for later on when we've talked about memory in some more detail. As with the 5-state model, there are additional exit transitions. If process is killed, regardless of whether it's in memory or on disk, then it moves to the terminated state. Familiar with these? These are our process functions, and we should be familiar with them. Fork creates a child process. Remember that the child process that is created is an exact duplicate of the parent down to its current execution state. So you will notice that we did lots of examples where we said, okay, the parent process calls fork, and at that point a parent process and child process are created, and they both start executing at the statement that is the assignment of the return value of fork, because we needed the return value there to differentiate between whether a particular thread is the parent process or the child process. And that's how we did it. That's why fork returns this process ID type, because that's how we differentiate which is which. Similarly, we said wait is how a parent process waits, see what the name did there, for a particular child process to finish executing, and we get back a status. We also will have seen, and probably if you did some of the exercises, you will have determined that actually returning a number through status as though we're trying to pass data through inter-process communication doesn't work the way that we hope that it works. That's okay. It is useful to be able to return a status, but we prefer to use different mechanisms if we actually intend for the processes to communicate in terms of inter-process communication. And the difference between wait and wait PID is wait will wait for any child of the current executing process that calls it, whereas wait PID allows you to specify that you would like to wait for a specific child process. In most circumstances that we were using this previously, we just used regular wait because there was no need to wait for a specific process ID, but the option was always there. And then there is exit, and exit terminates the currently executing process as we would expect, and it returns a value. That value may or may not be collected by the parent. It's possible that the parent doesn't care, and for a process whose parent is init, init most definitely does not care, and that's fine. That's exit terminates this process, and by convention a 0 exit is normal and a non-zero exit is something is wrong, and you can use the exit codes as a way of giving some sort of error code if you wish. It's not necessarily as good as writing a descriptive log entry, but it does accomplish the goal of saying, hey, I got error 7, what do I do with that? And we also talked about signals just a little bit as well. And kill, despite the name, is how you send any signal, not just the kill signal, to another process, including trying to terminate it for whatever reason. Raise is a way of sending a signal to ourselves if for some reason you want to do that. And then we discussed also in some detail the idea of signal handling. And so the third entry here is how you handle a signal, where you specify a signal handler. We'll actually see that later on in some in-class exercises. And then pause just pauses the current thread until any signal has been delivered, which is a way of waiting for something to happen. Although we learned later on much better ways of waiting for things to happen using things like semaphores. Just calling pause and what have you probably doesn't work as reliably as using an actual concurrency control construct. We also spent some time talking about the idea of deferring, blocking, disposition of signals, and so I included here as well how we configure a signal set and how we can create an empty one. We can add a signal to it, we can fill the set, so put all possible signals in the sig set, how we can remove one, and then we can set a mask. As you will recall with the mask, we're saying we're not interested in receiving certain signals. The idea generally is that this is supposed to be temporary, blocking those signals during a time in which it would be inconvenient to try to handle those signals. It is possible to abuse, right? It is possible to ignore signals that you should be handling and to permanently ignore them when you shouldn't be permanently ignoring them. The operating system doesn't really stop you. It just recommends against it. And we saw also that certain signals like sig-kill cannot be blocked or stopped or ignored, so adding them to the ignore set or something does nothing. That's a brief review of the signal functions. And you also, I imagine, remember something about threads, because we certainly spent a lot of time talking about it, and well, with good reason, right? And the term thread was a short version of thread of execution. And thread of execution is quite simply a sequence of executable commands that can be scheduled to run on the CPU, right? And every process has at least one thread, and could have multiple, right? It could have as many threads as we told it to create using pthread create, as we'll see a little bit later. Well, there's kind of no limit on this, right? We talked about the idea of fork bomb in the previous course, and we said, all right, at some point the operating system is going to stop you from creating more processes, but there's kind of no limit to creating threads. And at one point I tried to exhaust the number of threads on my machine, and it took quite a long time, and we were like multiple minutes in, and it was like, okay, never mind. There's no way I can run it out of threads in a reasonable time, and that's fine. Threads themselves have state as well as local variables, and most programs that we wrote in previous courses before ECE 252 had only one thread. Program code executed one statement at a time. Things got interesting when we decided to break that rule. And a multi-threaded program uses more than one thread, at least some of the time. And the program begins with an initial thread where main is, and we created it and destroyed additional threads dynamically. And I will show you this diagram, ancient and terrible though it is, and said, okay, in the ECE 150 model, we have one process, one thread. And then in the beginning of ECE 252, we learned about multiple processes with one thread per process, where we talked about fork and having communication between the different threads, between different processes using inter-process communication mechanisms. So we covered that sort of thing. And then we transitioned to the upper right corner where we talked about one process, multiple threads, and that was actually where we spent the majority of our time during that course. We spent a lot of time talking about creating threads and having them communicate all within the same process. With that said, nothing really stopped us from having the kind of organization that looks like the bottom right corner, where we have multiple processes and multiple threads per process. in which everything is on the table, right? We have our inter-thread communication plans as well as our inter-process communication to make it all work. Now, from the point of view of the operating system, it doesn't matter so much which organization the user program chooses. We just have to be able to handle anything, right? There's a distinct possibility that the authors choose one process with multiple threads, but there's also a possibility they choose multiple processes with multiple threads, and the operating system has to be able to handle that. That's okay, right? It's not dramatically different from the point of view of the operating system, as we'll see, but we do have to be aware that this is a thing. Now, in a process that has multiple threads, every thread has its own thread execution state. It has its saved thread context when it's not executing. It has its execution stack. It has its local variables. And it also has access to the memory and resources of the process that are shared with all the threads in that process. And we showed this diagram that showed like this. That said a multi-threaded process, right? The code, the data, the files are all shared, but each individual thread has its own registers, has its own stack, and has its own execution context, where we are in the execution of that thread. And threads are, as per usual, represented as a little squiggly line, as though it is a piece of thread that's fallen from an item of clothing. That's not really how they work, of course, but that's the traditional representation of one. Okay, and yeah, we also know that all the threads of a process share the state and the resources, so if one of the threads opens a file, well, everybody can use the file, and any of those resources can be shared, requiring our own implementation of some sort of concurrency control to try to make sure that things don't go wrong. Right. There is a performance risk trade-off in threads, and it is entirely possible to effectively crash your whole program by having one thread go wrong, whereas if we had a multi-process approach, one of the processes would crash, but the others would be okay. My expectation is this should be familiar, but if you wanted a sort of quick reminder, here are a number of the functions that we talked about related to managing threads. And we create a thread with pthread create, and pthread create takes a pointer to the pthread t structure. This is our management structure that is used. It's initialized here by creating the thread, but we use it later on in the various functions to interact with that thread later on after it has been created. And we could specify some attributes, and I said attributes defaults are fine because realistically, sort of at that level, we don't need to care too much about the attributes. Maybe in a more advanced setting, there are cases where it would matter, but for the most part, we are comfortable with the default attributes. And then we had void star start routine, which takes void star argument, which is a function pointer. We would give a function pointer here. And the function pointer has to have a void star return type and take one single void star argument. And then, we talked about how to successfully pass arguments to said thread. And one of the ways that we did that was using this void star arg thing at the last position in the function call. And whatever argument we pass there is provided to the function that we called. Now, in numerous circumstances, we said it is necessary to pack the arguments into a structure or an array of some kind, because it does feel a little bit limiting that the new thread is sort of limited to just the one parameter. But we could always create our own structure where we say, okay, this is a parameters type, and we pack everything that we need into the parameters type, and then we do it. In assignment questions, exam questions, sometimes we just use global variables for these things. That's not because, as I'm sure I said, it's not because it's good programming practice, because it isn't. It's because sometimes that's just faster. When the purpose of the question is to test sort of our understanding of how do we create and work with threads. We shouldn't spend too much time focused on passing the data in between them, because that's a subject for a different question, or it's not really relevant, or it would just take more time than the question has for us to work on it. So, okay. All right, but we know how to send an argument to a thread, and we know how to create one. And joining is how we wait for a thread, analogous to the wait call. And we specify a thread. You'll notice it's not a thread pointer, it's a pthread-t structure. This is one of those cases where, as I say, the spec here is a little bit inconsistent because pthread create takes a pointer, but pthread join doesn't. That's just something to pay attention to, and in the past I said you need to pay attention to the reference sheet, because noting that whether there's a little star there or not will help you to get it correct on the exam when you don't have the compiler there to help you out. Ideally, you do have the compiler to help you out, and it'll tell you, hey, did you mean to put a star here or an ampersand? But sometimes it doesn't catch that. In any case, join is wait for the thread that's specified by this pthread-t to complete, and when it is complete, then we will collect a return value, and we collect the return value by effectively updating the void pointer that is passed as the second argument here, and that's why it's void double star. That being the case, right, you don't have to. If you're not interested in collecting a value from this particular thread, that's fine. You can provide null as the last argument, and whatever value is just thrown away because you said you're not interested in it. We can only join a thread if it is in fact joinable, and by default threads are joinable, although you can change their attributes so that they're not. But if your intention is to make a thread not joinable, that's why there's pthread detach, and it means an attempt to join it doesn't work. And as I say, sometimes that's what you want. If a thread is fire and forget, you're never going to collect its value or anything like that, then calling detach on it is correct, because, well, you don't want to wait for it, so don't. And then we talked about cancellation, and cancellation was a very complicated subject, right? We went over a good amount of stuff just based on the idea of, like, well, cancellation is hard, so how do we do it correctly, right? Canceling a thread sounds good, right? It sounds like we should not do work that we know we don't need. If we're certain that this thread is doing work that's useless, the user has canceled the request, why continue with it? Part of the difficulty, of course, with this is that, well, cancellation can be kind of sudden from the point of view of the process or the thread being canceled. And that's something that we don't like, right? We don't want data to be lost, or we don't want memory to be left allocated when it should be deallocated, just because, well, cancellation occurred. So yeah, we have to be mindful about this sort of thing, and ultimately we will try to avoid it, but can't always. And for that, we talked about like test cancel, and that's how a thread will check and see if it has been canceled, and that is one way to terminate your thread, because it terminates the thread if we've been canceled. So it's not really test cancel; it's more like exit if I've been canceled, which is kind of unfortunate, but that's a little misleading, and it's possible to sort of get that wrong. But nevertheless, it is something that we understand if we read the specification. And part of the reason why cancellation is slightly a headache is the idea of cancellation type. And you can set cancellation type to either asynchronous or deferred. And we said that asynchronous is immediate. Like when a thread is canceled, it just dies at once. This is like using kill with the sig kill signal. In which case, well, there's kind of no coming back from that, and the thread just dies immediately. Probably not what you wanted, but it could have been, I suppose. And then there's deferred, and deferred does give the thread the opportunity to clean up and recognize this before it has actually been canceled. Part of the problem with that, though, is that there are a lot of cancellation points. And cancellation points are system calls or other functions that have an implicit check for cancellation, which may terminate the thread before you were expecting it to be terminated. And I mean, that's okay, right? The important thing to some extent is that the thread does exit, because it's possible for a misbehaving thread to not exit the way that it is supposed to exit. Yeah, the cancellation points kind of guard against that. However, to make sure that resources were returned, we said, well, that's why there are cleanup handlers, and we can push a cleanup handler and we can pop a cleanup handler, and we actually spent a lot of time talking about those. And so how do we do those things correctly? It's not easy and it's not perfect, but it is better than not trying to handle them. And then finally we have pthread exit, and pthread exit is used at the end of your thread to return a value. When we do that, right, we're sending it back to whichever thread called pthread join, assuming that thread is interested in collecting the result. Maybe they're not. One of the other things that we will have covered was the idea that sometimes for certain versions of the pthread library, the Valgrind or Helgrind is not happy with pthread join. It thinks there's a memory leak. And you can get around that by ending your thread with a return statement, which had the same effect as the pthread exit. This works okay because we have the idea of like return at the end of main terminates your program, but you could call exit at any point. And you can call pthread exit at any point in the thread, and that terminates the thread. So it kind of works the same way. So that's okay, right? For the most part, though, pthread exit is, in quotation marks here, correct. And it is the right way, again, right in quotation marks, to terminate a thread and send a value back to a waiting thread, even if Valgrind is not necessarily super happy about it. That's beyond our control and fixed in newer versions of the library. We just have to wait for them to be installed on our various servers. Okay. Anyway, if this doesn't seem familiar, I really would like to ask you to go back and review this sort of material from ECE 252. There are some further examples and longer breakdowns and longer explanations of all of these things. But the operating system is responsible for managing the processes and threads of the system. And if we don't have a good understanding of what they are and what are threads and how do they work and how they might behave, that obviously makes it much harder to actually carry out the task of understanding their management from the point of view of the operating system. So, like I say, please go back and review if this seems very strange and or unfamiliar.